Okay, so last week we looked at continuing our model by dissolving some ionized salts in some water. The question came up, was that a physical change or a chemical change? Well, the way we're able to determine that is by getting rid of the water. If we evaporate all of the water off and there's a new chemical sitting in the bottom of this beaker, well, then we would have a chemical change. But if it's the same starting chemical, we would have a physical change. So I evaporated all the water off, and we can see, look at that. That is the same stuff that we started with. Same here. We can see it on the bottom. One of them looks like there's more in there, but that's just because when it dries, it actually kind of fluffs up. Think of a cotton ball. So if I scramble this stuff up, it'll go into a very fine powder just like it started. So we can see that this was, in fact, a physical change. So these thermodynamic laws must have something to do with physical changes as well. Let's start looking at that. All right, so as it currently stands, this is the model that we have. We have temperature is the motion of molecules, that it's that average kinetic energy. We can measure energy in joules. However, we don't really know how much a joule is, so we can't quite use that yet. We know that these thermodynamic laws are applying to both physical and chemical changes. We established that just 2 minutes ago. We need to figure out our model for what these chemicals look like, and we need to look at kinetic energy versus potential energy. We've started to investigate that, but we need to get into it a little bit more. Now, after we get this model figured out, what we're going to do is we're going to finish looking at the laws of thermodynamics. So far, we've only needed to establish one of them. The first law, energy is conserved. That means that energy is not going to be created, it's not going to be destroyed, it's only going to change forms, again, like this kinetic versus potential energy. That's really what we've established so far, that we're constantly moving energy between potential and kinetic types. Now there's 3 other laws of thermodynamics. You see this 0 here? There is a 0th law of thermodynamics. It's really fundamental. We'll look at it later. It seems a little confusing that there's a 0, 1, 2, 3 instead of 1, 2, 3, 4. It's not that big of a deal. So we're going to get more into these, and we're going to finish up our model here. So in order to finish rounding out that model, we really need to establish 2 things. One, a model for our chemicals. Thankfully, we're going to be able to use Lewis dot diagrams. We've already delved into that. We're just going to need to revisit that topic in order to round everything out. 2, we need to figure out exactly how much energy is 1 joule of energy. Now, the thing to keep in mind about a joule is that it's an arbitrarily defined thing. What does arbitrary mean? Well, what that means is basically we made it up. It's not based on anything exact in the universe. It's we needed a way to measure this, so we decided let's look at it this way, and we agreed on it. It's something that humans have come to agreement on. Another way to think about that is like a meter stick. 1 meter is 1 meter, but there's nothing in nature that says, hey, this is a meter. It's something that we decided and then defined and went, so this is how we're going to measure stuff in meters. This is how long a meter is now. So a joule is the same way. There's nothing in nature saying, this thing is a joule. This thing is an amount of energy. It's us going, this is how much a joule is, and we're going to use it to define things over here. So we need to look at that definition and be able to track those changes. So we're going to use the same physical change that we looked at last week with the ammonium nitrate and the potassium hydroxide, except instead of just doing 1 of each, we're going to do 5 of each so that we can look at the data and look at how these things change. In each one, I'm going to be using a different amount of mass, and then we're going to track our temperature changes. So what we're going to do today is I'm going to go through that lab. You guys are going to fill out this data table, and then tomorrow we're going to go through and we're going to graph the mass versus a change in temperature. Then on Wednesday, we're going to go through and we're going to do some math, and we're going to actually define how much a joule is. We'll be able to see how much energy is being traded in each of these chemical changes, or physical changes. Sorry. So what is this symbol right here? Well, the interesting thing about thermodynamics is it doesn't really matter what our starting temperature is. It really has no bearing on anything. Our starting temperature could be 50, it could be 20, it could be 10, it doesn't matter. Our final temperature is going to change based on what our starting temperature is. So the thing that we really need to track isn't what our starting or final temperature is, it's what the difference between those two is. So in most of these reactions, I think room temperature is about 21 degrees right now. I measured it a little bit ago, but it fluctuates by about a degree. So let's assume that it starts at 21 degrees. If it changes by, let's say, 5 degrees to 26, it goes up to 26, well, what I really care about is the change in temperature. So I can take 26 minus 21, and that will give me 5. So my change in temperature would be 5 degrees Celsius. That's what we need to get so that we can graph this and actually see how this stuff changes. If we just use final temperature, our graph is going to look kind of funky. So we want to make sure that we're calculating out delta T. That's what that triangle is. That's called delta. It's the Greek letter for D. So delta is the Greek version of D. And whenever you see this in science, it just means the difference, the change in something. This is very common in science. It's more common in higher level mathematics. You might see those junior and senior year of high school, but you're going to see this a lot in science. So delta T, this triangle T, means the change in temperature. That's always going to be the final minus the initial. Okay? Great. So in each of these, you're going to take your final temperature, subtract your initial temperature to get your change in temperature. When we graph this, what we're going to be able to look at is what is the relationship between these values. Because if I go up from 5 grams to 10 grams, I have doubled my mass. Is my change in temperature going to double? That's why we need to look at the change in temperature, not just the final temperature. Because if my change in temperature goes from 5 to 10, that's twice as much. It doubled at the same rate that this doubled. There is an equation in there. That's going to help us define some variables. But my final temperature wouldn't double. That's why we really need to look at this change in temperature. Okay? Okay. So I've already got everything measured out here. I've got 5 beakers with 50 milliliters of water in each one. And then I have my masses of chemicals already sorted out. So this is my ammonium nitrate. I've labeled, see I've labeled my masses, just keeping things a little organized, and then I've got another layer of tape here so I can document the final temperatures. You guys are going to be documenting those in your actual Word documents. Here I've got, it's fine, I've got my potassium hydroxide. So there I've got all of those marked down as well. Notice that the potassium hydroxide goes up to 80 grams. Ammonium nitrate only goes up to 59. That's because 59 is the maximum amount of ammonium nitrate that can be dissolved in 50 milliliters of water. It wouldn't change anything to have more. So the way I'm going to do this is I'm going to make use of my magnetic stirrer here. So if I turn this on, this guy stirs automatically. It'll make things a lot more convenient for me. I've got my temperature, my thermometer right here. And so we're going to get started right away. First we're going to use the 5 grams of ammonium nitrate. So when I turn the stirrer on, it'll stir things up. I'm going to move it over a little bit, make room for my thermometer. And then just give this a sec just to get the initial temperature. It looks like we are at 21 degrees. 5 grams of ammonium nitrate going in. You should have already marked, you should be marking the 21 degrees as your initial temperature. Our final temperature is 16 degrees Celsius. So I'm going to mark that on my tape here. So 16 degrees Celsius for temperature final. All right. So I'm going to stop this, switch it out. We are reset to 21 degrees for our initial temperature, and I'm going to put in 10 grams of ammonium nitrate. That's 10 grams of ammonium nitrate. We bottomed out at about 10.5 degrees Celsius. Okay, now we're doing 20 degrees, or 20 grams of ammonium nitrate. So I'm going to turn on my stirring first. And 10, and 20. I'm going to turn up the stirring nice and far. Our starting temperature was 21 degrees again. Okay, we finished up at 3 degrees. 3, just down to 3 degrees Celsius. That was our final temperature for the 20 grams of ammonium nitrate. Now, just some casual observations. This actually cleared up a lot. Even with 20 grams of ammonium nitrate, this liquid is very clear. I can see a little bit of stuff still floating. That's just, it's not quite all dissolved, but the majority of it is. It feels very cold to the touch. It's like holding an ice cube. Okay, I've got my temperature reset. Next up is the 40 grams of ammonium nitrate. So let's go ahead and turn on the stirring and pour it in. Okay, my temperature here bottomed out at negative 6 degrees Celsius. Now I'm noticing that on the outside of this glass, it's starting to fog up, just like a glass of iced tea or a cold soda would in the middle of summer. It's very cold to the touch. Like it's very, very cold. Let's see. I've still got some ammonium nitrate left over in the bottom. You might not be able to see that, but it's there. So I wonder, this makes me wonder if that 59 grams is going to fully dissolve. Okay, and last but not least, 59 grams of ammonium nitrate going in. So I'm going to turn on my stirring. My temperature is back up to 21 degrees Celsius to start with. My stirring is on. I'm going to pour it all in. Okay, so our lowest temperature here is going to be negative 7 degrees Celsius. That's interesting. Why did that not change as much? Any ideas? If we just take a second to notice this, I have a lot of leftover material that did not dissolve. Look at that. You can see that. All that right there, all that white stuff is still undissolved ammonium nitrate. I wonder if I left it in here just like this, how long would it stay cold? Okay, it's been about 10-15 minutes and the temperature is still staying down, even though there's still a lot of ammonium nitrate that's left in here that hasn't dissolved, and the temperature is staying down. Why do you think that might be? Okay, next up we've got potassium hydroxide. So I've already got this measured out as well, 5, 10, 20, 40, and 80. So we're going to do the same thing, and I'll have you zoomed in right here. So we're going to start with the 5 grams. Their initial temperature is going to be 21 again. Good consistency here. So let's go ahead and turn on our stirring and put in our 5 grams. Alright, and our temperature has increased to 25 degrees. So our final temperature is 25 degrees Celsius. Let's get it ready for the next one. Alright, and we're back at our starting temperature of 21 degrees. So this is the 10 grams of potassium hydroxide. Going in, stirring it up. Alright, this one maxed out at 31 degrees. Back at 21 degrees Celsius for a starting temperature, and this is going to be 20 grams of potassium hydroxide. Okay, and this one maxed out at 42 degrees Celsius. 42 degrees Celsius. Alright, next one, 40 grams of potassium hydroxide. This one actually is at a starting temperature of 22 degrees Celsius. Turn on our stirring, pour it all in. Alright, our maximum temperature here is 62 degrees Celsius. Now you may not be able to see this at home, but this is getting quite warm. I'm seeing some condensing on the outside of the beaker. When I hold it, it's very hot. I actually can't hold it for very long. Alright, once again we're at a starting temperature of 22 degrees Celsius. This is our 80 grams of potassium hydroxide. You may have noticed I'm using a larger beaker for this one. This is a good time to think about what temperature do you think this is going to get up to? You've seen everything so far. Has it gone up at an even pace? Do you think you could predict this final temperature? What do you think this is going to be? Alright, our final temperature is 94 degrees. 94 degrees Celsius. Is that what you expected to see? Now this is getting so hot that it's actually almost to boiling. I can barely touch the beaker, and there's a lot of steam coming out. There's a lot of condensing on the side here. So this really significantly increased the temperature. This was a lot of increase. All right. Here are our final results for our data table. We've got for the ammonium nitrate, starting at 21 degrees Celsius for everything. And then our 5 grams was 16 degrees Celsius. 10 grams was 10.5 degrees Celsius. 20 grams brought us down to 3 degrees Celsius. 40 brought us down to -6. Make sure you use that negative when you're calculating your change in temperature. And then last, our 59 grams brought us down to -7 degrees Celsius. Okay, and then our potassium hydroxide, 5 grams brought us down to 25, 10 grams brought us down to 31, 20 to 42, 40 to 62, and 80 to 94. The only difference here, our initial temperatures for the first 3 were all 21, and for the 40 grams and the 80 grams, they were 22 degrees. So go ahead and fill out those tables. Tomorrow we will graph